So we will take notes, but we're going to start with this little worksheet, 8.3 here, 2/24, 2020. And today we're talking about the number E. And the number E is a number, much like pi is a number. So pi, you know as what? What is pi? 3.14159. And you have a button on your calculator. Does it stop right there? Or does it keep going? It keeps going, yeah. We call that an irrational number. It is an irrational number. Irrational means not a ratio. Ir as in not. So not a ratio. It means you cannot write it as a fraction. You cannot write it as a ratio of two numbers. E is much the same. And so this little worksheet that has that 8.3 side is going to tell us about E and where it comes from. So I do this in all of my classes because I think it's really, really useful. This just happens to be a pretty good worksheet here. So suppose you live in a country where the rate of inflation is so great that savings accounts are offered at an interest rate of 100% per year. So wow, 100% per year is the interest rate, compounded in times per year. And N is allowed to vary. So you can see we have different values for N. And suppose you invest $1,000 in a savings account. Well, that would be great, but I actually want to do this for the purposes of actually finding out the value of E. So we're going to just invest $1. We're going to see what happens to our $1. So go ahead and change that. So suppose we take $1 and we invest it in this savings account. So we're going to use the compound interest formula. We learned this formula last Tuesday. And P was the principal. What is our value for P? What is our principal amount that we're using? $1. Okay, we're taking $1. We're going to see what happens to our $1 investment. Then we have 1 plus R over N. What is the R value? R stands for rate, okay, and our interest rate is 100%, but we don't use percentages, so as a decimal, that means 1. Yeah, so we move the decimal 2 places over, and we get a value of 1 for the R value. And then N is going to change, and T, we're going to find the amount of money in the account after 1 year. What is our value for T? 1. Yeah. So you're going to need your calculators out, and we're going to see what our amount is after 1 year when we start with $1 single that's got an interest rate of 100%. So in your calculator, we have a p-value of 1, and then 1 plus, our R is 1, over, first we're going to see what happens when we compound annually. So this is an N value of 1 to the N times T. So that's 1 times 1 year. So 1 annually for 1 whole year. So you should have your calculator out, and you're going to type these things in. And you need to do this because it's important that you know how to use your calculator properly, okay? So most of you have Casios, so I'm gonna use the Casio. If you have a TI, it should be pretty easy. So I'm gonna go ahead and type this into my calculator. 1 divided by 1 to the, what do I have to do with this 1 times 1? Put parentheses around it. Yeah, we have to tell the calculator that it's all up in the exponent position. Of course, you could multiply 1 times 1 in your head is fine, but okay, we get $2. So after 1 year, if we compound it 1 time, we're going to have an extra $1, which is kind of nice. Hey, it's free money, right? So I'll take it. All right. So now what happens when we compound quarterly? So now my N value is just going to be 4 in both places. So we have our starting dollar, 1 plus 1 over 4 to the 4 times 1. So I'm going to go ahead and type that in. And again, this is really about, can you use your calculator? This isn't hard. but learning how to use your calculator is the biggest challenge. So you have to use it. You have to practice. What do we get if we compound 4 times per year? $2.44. Hey, how about that? So what happened when we compounded 4 times? We got 44 more cents. That's exactly right. Hey, I'll take free money. Okay, an extra 44 cents. All right, so now we want to see what happens when we compound 12 times per year. So we're going to change the ends into 12s. So 1 plus 1 over 1 divided by 12 to the 12 times 1. So I'm not going to put my calculator down here anymore, and you're going to type it in, and you're going to tell me what it is. All right, what happens when you compound 12 times per year? We get $2.61. Should be 61. All right, 2.61. All right, 2.61. So again, so what's happening the more often we compound? What do we get? We get more money. Yeah, so the more we compound, the more money we make. Now it seems to be decreasing. When we compounded 4 times, we got an extra 44 cents. But when we compounded 12 times, we didn't get a whole extra 44 cents again. We're getting a little bit less each time, okay? All right, so now we want to know what happens when we compound daily. So we're going to change the ends into 365. 1 divided by 365. So go ahead and type that into your calculator. All right, what do you get when you compound 365 times? 2.71. Good. Again, if you are not getting these values, you need to let me know now so I can fix it. All right. Okay, so then we want to know what happens if we compound hourly every single hour. So that would be 8,760 times a year. 8,760 times every single year for a year. 8760. Oops. All right, what do we get when we compound 8760 times? Oh, that's kind of stayed the same, didn't it? This was 2.714. This is 2.718. So, we're getting a little bit less and less each time, It seems to be leveling off, so to speak, okay? Let's see what happens when we compound 525,000 times. 525, 600. That's every minute. That's a lot, compounding every single minute. All right. Oh, what's that? Kind of the same, isn't it? 2.718. This was 181. This is 182. All right. So, ladies and gentlemen, it seems like compounding more often gets us more money, but it seems to be sort of approaching this number. It's sort of starting to stay the same. Okay. Now we're 3 decimal places is staying the same, and that 4th is changing. But that, I guess, imagine would start to be the same too. Well, ladies and gentlemen, this is the value of E. As we compound more and more frequently, as N increases, the situation approaches what banks call continuously compounding. And as we do that, all of this stuff, pretty much most of this formula transforms into what we call the number E. E is 2.7182. It goes on forever and ever. You have an E button on your calculator, so we want to locate that E button now. And it is, on both calculators, you have a natural log button and LN button. So on the Casio, you see the LN button, and right above it in yellow is E to the X. So we would want to do E to the X, and then just type in E to the first power, and you can see you get 2.71828. On the TI, we have the LN button over here, and just above it is the E to the X button. So we want to do second E to the X, E to the X, and again, just E to the first power, and we see that we get 2.71828. Okay. So for E is a very special number. It's a naturally occurring number. That's this, some dude figured that out, 1,000 years ago. Not, this was before the time of calculators, but he just realized that this number just sort of happened. So we call it a natural number because it occurs naturally. It occurs all over the place. So I have a little saying. So I'm going to ask you a lot, what is E? And your response is not quite 3. So what is E? Not quite 3. And the reason we do that is because it rhymes. Okay, what is E? Not quite 3. And we want to know that because it's good to have an understanding of about what it is. But it is not quite 3, and that's going to help us graph. And so we have one formula that you guys are going to learn. We're going to use it tomorrow, and it's the continuously compounding formula, and it's derived from this one that we just did, except like all of this stuff turns into an E, and that is this formula right here. So we're going to talk about this formula tomorrow. You should write this down in your notes. So if you've got your notes out, continuously compounding interest formula is A equals PE to the RT. We're actually going to use it tomorrow. It is a very common formula, definitely one you want to memorize, but it comes from what we just did, which is why I like deriving it. So you can see from the previous formula that we had, the P's still match up, and almost all of this turns into that E value. The only thing we need to account for are changing R values and time. And so it becomes P times E to the RT, and we're going to use that formula tomorrow. Today, we're doing some more graphing. Today's super easy, and again, you want to have your calculators out. And so, like super easy, like your worksheet takes like 10 minutes, and I'm going to put a note for next year that says, hey, we can do way more than this. Example 1, tell whether the function is an example of exponential growth or decay. Example 1, tell whether the function is exponential growth or decay. Tell whether this is an example of exponential growth or decay. Okay, we've talked about exponential growth and exponential decay. We did that little fun activity with the M&M's decay on Wednesday. If you weren't here, you missed M&M's in class. It was super fun. So exponential growth. What does exponential growth look like? I had a special name for that graph. What was that graph? Superman, yeah. Exponential growth has a horizontal asymptote, and it's that Superman shape. And that Superman shape really just means that as we move along to the right side of the graph, it's pointing up all the way to positive infinity. It's growing really, really quickly. But it turns out there's also another shape that is also exponential growth, and that might be something that looks like this, where it's actually going down to negative infinity. It's a flipped upside down graph. It's just this graph that's been flipped over. And it's still growing. We call this growing in the negative direction, where it's just growing more and more and more negative. So this is also called exponential growth. Exponential decay is what we looked at last Wednesday with our M&Ms. And exponential decay has, that's a Superman coming in for a landing shape. And that is that it's approaching 0. It's getting closer and closer to the x-axis. So this is Superman coming in for a landing. It's just getting really close to the axis. And again, there's actually another shape as well, which is this. And that's approaching from underneath. We're still getting closer and closer to that x-axis. So both of these are decay. Decaying to nothing. That's what that means, okay? So we're either growing to positive infinity or negative infinity, or we are decaying to 0. And so the easiest way to do this stuff, when in doubt, graph it out. So all of these have y equals, so we're just going to go ahead and plug these into our calculator and look at the picture. And so when you're typing these into your calculator, everything that's in an exponent, if you have a Casio, you need to make sure that you put it in parentheses so that the calculator knows that all of that is upstairs in exponent land. I'm going to go ahead and go to my graphing menu. And I'm going to type in 2 and then my E button, which is in yellow. So Shift E to the, and then I'm going to type in 4x. Your X button is underneath the alpha key, so make sure you do that. And then you can go ahead and graph that. And that's a fair graph. The Casios sort of do an auto graph. But that's the basic shape of it. It's growing to infinity. And don't think that it stops right there. It's actually just really, 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 really close to the axis. So it is more like that. That's what it looks like. Is that growth or decay? Growth. That would be exponential growth. So we're just going to write growth. When in doubt, graph it out. That's what those calculators are for. Over here, what do you think this one's going to be? Decay. All right. Let's look. I'm going to go ahead and exit. I'm going to delete my equation. Delete this one, rather. Okay. In my Casio, I'm going to type in 1/3, 1 divided by 3 in parentheses. And then e to the negative 2x. Again, I'm putting in parentheses e to the negative 2x. And you can go ahead and graph that. There we go. Growth or decay? Growth or decay? Decay. It is decay because as we move to the right, you can see it's really tall, but as we move to the right, it's getting closer and closer to 0. So that is decay. Yep. You didn't get that. Did you type in the negative? Oh, you put parentheses around the wrong thing. So let me go back. Whoops. There you go. See how I typed that in? So you need to change your viewing window. So go to the viewing window. It's yellow. ST. All right. And now exit and graph. Got it? Okay. Anybody else have problems with graphing? Yes. You need to go away. So that's a window error. So you need to do a two standard. Did you have another?
Oh, yeah, sorry.
You have
Is that what you need?
All right, anybody else? So you are pressing just that button. Oh, you're in parametric mode. So let's delete your equation. You want to go to type. Yeah. You push the type F3. Exit. Now push type
Invalid dimension.
F3.
What does that even mean?
That means your window is off. You need to press zoom standard.
You're a boy, you're
Now you can. Yeah. All right. Very good. So some of you in your on your TIs, you might be getting errors, or if you don't see this window, Casio's automatically draw a window. For both calculators, if you're getting a weird, and like for TI it says invalid dim, okay, that means that your window is set up wrong. And you want to just do a zoom standard. So you push zoom and standard, that's going to take you to standard normal window. It'll reset everything. On the Casio, we have a very similar thing, and you would do viewing window. V window is yellow, so we do shift viewing window. And this one right here in the middle is standard. And you would just reset it to a standard window and exit and draw, and it'll take you to a regular window, okay? And regular being -10 to the left, 10 to the right, 10 up, 10 down. So yours isn't because it's flat one isn't highlighted. So you want that. Alright.
No, that's pretty good.
Okay, we're gonna do some more of that in just a minute, but let's go on. Here we go, example 2. Graph the core, then shift, state the domain range. Which E did you use? The yellow one? Okay. And viewing window.
I just got hired. Where? I just need to where.
Oh, see, it should be from -10 to 10. So we're gonna press standard. So press F3. F3. Alright, so reset things. Okay, so now exit. Yeah. Alright. Graphing the core, then shift, state the domain, range, and horizontal asymptote. All of these we can graph by hand, which is what we're going to do. And then, of course, you could check on your calculator. I am pretty specific and ask very specific questions about domain, range, and asymptote. So those are the things that you need to know, and that comes easily when we do things by hand. So first it says graph the core. The core is always just from y all the way to the x, and that is our core function. These are Superman graphs, and so they all graph really easily. Just looking at the core, we're going to take a really easy XY chart. And we did this all last Monday. Same exact concept, except we have a base of E instead of a base of 2. What is E? Not quite 3. Ladies and gentlemen, what is E? Not quite 3. So we're going to plug in some really easy values for X. I'm going to plug in a 0. If I plug in a 0, that's going to be E to the 0. What is E to the 0? Nope. 1. When in doubt, use your calculator. So if you aren't sure, look, we can go to our calculator, e to the 0. E to the 0, whoops, is, oh, sorry. All right, e to the 0 is 1, okay? You can always plug things into your calculator, but any number to a power of 0 always equals 1. If we plug in a 1, what's e to the first? What is e? Not quite 3. It's 2.71828. It's not quite 3. And that's what we can graph by hand. So I'm going to use 0, 1 for my first point, and then 1, not quite 3, just under 3 on my graph. Not quite 3. Not quite 3. And this is my basic Superman shape. This is called a natural exponential function. Once we graph that core shape, then all we have to do is shift it. How does this shift? What does x plus 3 do to the graph? Left 3, and what does the minus 5 do? Down 5. Very good. So I'm going to take these 2 points, and we're just going to count left 3, 1, 2, 3, down 1, 2, 3, 4, 5. Left 1, 2, 3, down 1, 2, 3, 4, 5. Now, before I connect those dots, we want to know the horizontal asymptote. Really important, always, whatever that k value is. So I'm going to draw in that horizontal asymptote first, and then draw in my Superman shape. So now when I look at this, the domain is always negative to positive infinity. The range is the thing that we have to be careful of. What is our lowest value and what is our highest value? Negative 5 all the way to infinity. Yeah, so negative 5 all the way up forever to infinity. And parentheses around those. Okay? Questions on that? Again, it's something you could check in your calculators. Delete. So I could type in e to the, and then in parentheses, I'm going to do x plus 3. And then on the outside would be my minus 5. And so if you're using Casio, it's pretty tricky. You have to tell it what's in the exponent using parentheses. And then I can draw that, and you see a pretty good graph, very similar to what we drew. Okay? You can also, whoops, oh, okay, sorry, I'm going crazy. Here we go. You can also do trace, so second trace, and I can check my value here at negative 3, and it tells me it's negative 4, which is exactly where I am on my graph as well. Okay, trace is awesome to check ordered pairs. All right, let's look at letter B. What does this negative do to our Superman graph? It doesn't make it do decay, actually. What does a negative out in front do to functions? It flips it, yeah. This is a reflection, so it's going to take our Superman curve and turn it upside down. But the nice thing is we can just add it into our core, and it'll work out perfectly. This is a flipped Superman graph, but let's see what happens to our values. So this is negative e to the x for my core, and again, I'm just going to plug in 0 and 1. So we have negative e to the 0. What is negative e to the 0? Negative 1, yeah. E to the 0 is 1, but there's a negative in front, so it's negative 1. And then we have negative e to the first. So what is negative e to the first? Negative 2.7, negative not quite 3. So again, these are just nice ordered pairs, 0, negative 1. and 1 negative 2.7, negative not quite 3. So this is our flipped upside down Superman graph. So this is still exponential growth, but it is growing